All right, we are going to now work through a Gaussian problem with a different type of symmetry, and this will be cylindrical symmetry. I want you to notice that the end view looks the same as spherical symmetry, of course. That cross section would look the same, but the side view is noticeably different. And in the case of cylindrical symmetry, we need to consider both views. You'll see why as we work through the problem. So give yourself some time to take this problem in. It's also written and posted in Canvas. So um, look at it there. And then it's written down here. So you might want to pause the video and check it out. Draw your diagrams in. Draw those diagrams when you're doing these Gaussian problems. Draw your diagrams large enough that you can easily label stuff. You can easily insert your Gaussian surface and make it very clear what that surface looks like. So our situation here, let's talk through it. We have a coaxial cable. Both of the pieces of this coax cable are cylindrical. So notice that. So we have an inner cylindrical conductor here, and then we have an outer, it's coaxial, which means the axes line up, right? Outer conducting cylinder there. It's a pretty thin conducting cylinder, the outer one. They don't touch each other, so just assume it's mounted on some kind of insulating supports. The outer conductor has no net charge, and the inner cylinder has some uniform lambda. All right. So the first thing, our first job is to determine the electric field in all regions. Then we're going to graph E as a function of R. And then we're going to find the induced charge on the outer shell. So in general, in Gauss problems, this is how it goes. You use Gauss in order to determine E field for highly symmetric situations. And then you can also use Gauss to find induced charge, as we did in our spherical example. So if we're finding it in all regions, that means that we can maybe start by thinking about the region R less than A. So for R less than A, whoops, we are inside that inner cylindrical conductor. So I know that there my E field equals 0, and that's by the charged isolated conductor theorem. Okay, you should be feeling fairly comfortable with that at this point. So the next region, then, the region that's really of interest, a little more interesting anyway here, is R between A and B. So let's look at that now. This region here. So the region that I'm looking at, that's the region that I'm going to put my Gaussian surface into. So I'll go ahead and put my Gaussian surface right in whatever region I'm analyzing. Now I'm drawing a circle. Okay, a circle's not a surface. So you got to think about what kind of Gaussian surface you'd want to use. It's a cylinder here. So I'm going to use a cylindrical surface here, radius r. This is why the end view is not sufficient for cylindrical symmetry. That's why you need the side view as well. So in the side view, I'll go ahead and draw in my Gaussian surface here. It's a cylinder. It's a finite cylinder. We're told in this problem that this cable is long. This goes in front. That this cable is long. So we don't know how long it is. We're just going to assume it's really long. I let it kind of go off the page with dashed lines. That's fine. Our Gaussian surface has to be a finite length, though. Remember, it has to be a closed surface, right? And we have to be able to integrate over the entire surface. So it has to be very well defined. So here's my Gaussian surface. It's a cylinder of radius r, and then let's say it has some length L. In order to define a cylindrical shape, I need a radius and I need a height or length. So that fully defines my cylinder. So notice that that is kind of interpret that there as a closed cylinder. Okay, so it's like enclosing something. All right, so now in Gauss's law, one of the things that we need to figure out here is we need to figure out our flux and our enclosed charge. So for this case, what's my flux going to be? Well, in order to figure out flux, we have to think about dA and we have to think about E, right? So dA is easy. dA is always based on how I define my Gaussian surface. So dA is outward normal to my Gaussian surface. So on the curved surfaces, it's going to be radially outward. And then on the end caps of my cylinder, it's going to go along the length of the cylinder like that, right? So I'll just draw in some different DAs here for you to get the idea of that. So DA is everywhere outward normal. And because you always use a closed surface as your Gaussian surface, outward normal is non-arbitrary. There is a definite outside and inside to a closed surface. Okay, so we got our DAs in. Cool. Now let's think about our E's. So E field. Now, this is a positively charged rod, right? We're told it's positive, it has positive lambda here. The outer cylinder has no net charge, but I know this is a positively charged rod, so I know what I'm expecting for E field here is radially outward. I know that's what I'm expecting for E. So I'm going to have this radially outward E field. I'll draw in a little bit more of it. And we want to kind of think about the idea that like we're capturing some of this, right? The idea of flux is that we got to think about what parts of E are actually permeating through our Gaussian surface. That's what the flux is all about. So if I look at this, I can see that actually the only E field that's getting through my surface is the E field that is parallel to dA. The radial E field is getting through my surface, right? That's parallel to dA. The end caps of my, let me shade these in. The end caps here of my Gaussian surface have no E field going through them at all because I have a right angle between E and dA. So there's absolutely no flux through those end caps. All the flux happens through what I would call the curved surface of the cylinder. All right, so the way that we can think about that then is when we're considering our integral here, E dotted in with dA, we have our E, and now the only area here that actually contributes is going to be the curved surface area, not the 2 pi, not the pi r squared areas on the end, right? But just the curved part. So just the curved part is 2 pi r L. That's it. Okay. So there we have that contribution, and that's all we have for our flux. We can calculate our Q enclosed. So now look at your diagram. What charge am I enclosing? Well, I'm enclosing this part of my rod, right? Some length of rod. So I can call that Q enclosed then lambda, charge per unit length, times L, the length I'm enclosing. So now I have my phi, I have my flux, I have my Q enclosed, so I can write out my Gauss's law statement, which tells me that epsilon naught times flux, which is E 2 pi RL, is equal to my enclosed charge. And then I take that equation and I solve it for E, and I get lambda over 2 pi r epsilon naught. So this is the magnitude of the E field for R between A and B. So notice a couple things about it. Notice that it goes with 1 over R, not 1 over R squared. That's different from spherical symmetry, right? You're seeing a characteristic that's more of cylindrical symmetry here. Notice also that L, the length of our cylinder that we defined as far as the characteristic of our Gaussian surface, is gone, as it should be. The Gaussian surface we choose, which is an imaginary analytical surface, should not affect nature. Yeah, so it shouldn't affect the outcome of what I get for E here. Okay, so let's move on. We've looked at R less than A. We've looked at R between A and B. So now let's look at between B and C. And between B and C, we can see that we're inside conducting material again, right? So if I'm looking in this region here, I can see again E equals 0 by charged isolated conductor theorem. Okay. And I think I'm going to actually move this up here instead. Get it out of our way. Okay, cool. So we're done with that between B and C. And then the next region of interest to us is looking at R outside of C. So let's do that now. In order to analyze that, of course, we need to place our Gaussian surface in the region we want to analyze. So we put our Gaussian surface out here outside C. Gaussian surface has some radius r. What does it look like in this other view? Again, it's a cylinder, well defined here, radius r. This is the Gaussian surface that I'm drawing in, keep in mind. And again, I can just go ahead and call that length there L. That L, defining the cylinder in total is important in the intermediate steps of the problem. So it's not something you can ignore. Yes, it's going to go away, but that doesn't mean that it's not necessary to use this method to solve the problem. Okay, so now we're outside, and at any external point here, I want to think about, let's go back and consider our flux again. So my flux here, what's that going to look like? So in order to do that, we're going to consider dA again. And dA does the same thing. Outward normal everywhere. So the question then is, what does my E field look like outside here? And you might already have some idea about that, since this problem has some aspects in common with the spherical problem that we did before. So again, we'll look at this a little bit more closely as far as why. Remember that this is a positive lambda, that inner cylinder. And it turns out that out here, we have radially outward E field. Okay, so my E field is radially outward everywhere. So I'm going to have the same thing happen that happened before, and that is the contribution of E to my flux is only going to be along the curved surface of the cylinder, that the end caps of the cylinder here, I will have no E field going through those end caps. Same thing, I have a right angle between dA and E for my end caps. Okay. So then if I'm going to consider flux here, we're going to look at the same thing that we did before, and E dotting into dA again is just going to give us E times 2 pi RL. And again, that's because the 2 pi RL is the area of the curved surface. We don't include the pi r squareds, the end caps, because no E field flows through them. Okay, and then my enclosed charge. What am I enclosing? The outer shell, remember, has no net charge. So again, I'm just enclosing lambda L. So you can see that this is going to give us the same result that we got last time. So if I plug this into Gauss, epsilon naught E 2 pi RL is equal to lambda L. That gives me my electric field lambda over 2 pi R epsilon naught. Okay. So again, that's the same as the result we got for between the cylinders. That's not, always true, but it's true for this particular problem. This applies to R greater than C here. Okay, so now let's do a quick graph. This problem wanted us to do a graph before we look at the induced charges. You know the induced charges are going to be part of what's going on with the external electric field here, because we have the outer shell as a neutral object, right? There's no net charge, yet we have an electric field that exists out there. And one of the cool things about Gauss is, Gauss in and of itself, right, it tells us, it relates the flux to enclosed charge. And that reminds us that whenever we're enclosing charge in our Gaussian surface, whenever we have a net charge enclosed, we're going to have non-zero flux. We can count on that. So it's pretty simple. That's nice in that way. Okay, let's look at our graph. So we are graphing E versus R, and they told us they want us to go to 2C. So let's consider A is pretty small, I guess. And then we're out to B. C is pretty small, pretty close. I'll kind of exaggerate a little bit here. And then that would make 2C somewhere like here-ish. Okay. So let's think about this graph. Now, cool. I'm going to do this in maybe a different color for the contrast. Between 0 and A, we're inside that conductor. Let me crank up my thickness. Okay. Between 0 and A, we're inside that conductor. So that's at 0, between 0 and A. And then between A and B, the function goes with 1 over R. And when you're thinking about where to start it, remember the function. Let's go back and look at that function for just a second. It's lambda over 2 pi r epsilon naught, right? So let's grab that. And put it on our next page real quick. Oh, okay, never mind. Well, I'll just write it. Let's remind ourselves what that looks like. So that's going to be E equals lambda over 2 pi r epsilon naught. Okay, so this is what I'm looking at for the regions of free space, not inside the conductor. So we've got 0 between 0 and A. And then at A, what the idea here is that you'd look at this expression and you'd pop A in for R. So you could be able to figure out exactly, it's not infinity, it's not 0, right? It's some value. So there'd be some value where we would start, and I'll just go ahead and make that value, say like right here. Okay. And then this would be, there'd be some boundary issue stuff. We're not going to spend a lot of time on that. We'll just go ahead and draw it as a discontinuity right now. And then we're going with 1 over R. So what is that shape? There's some curvature to that shape. I'm just going to kind of freehand. And then between B and C, now we're back inside the conductor. That's the outer conductor shell. My electric field goes back to 0 there. And then as we go after C off to infinity, it's kind of as if that function just has a little missing gap in it, really. And then this would kind of go on there. So that's what my function would look like. It would go with 1 over R for the free space regions, and then it would drop down to 0 when you're inside the conductor. I think it's important to know that. You could go back and look at the spherical problem and make a similar graph. For any of the Gauss problems that you want to kind of have this insight into, graphing E versus R is useful. Okay, the final part that we're going to work on here is looking at our induced charge. So when we look at induced charge, you might remember from the problem we did before, we're looking for the induced charge on the outer cylindrical shell. How we do that, we need to use Gauss for that. So we would place our Gaussian surface inside the conducting material. So this is like this really narrow little band here between B and C, but that's where I'd place my Gaussian surface. And I'm not going to draw the side view because I think we've got it now. So I place my Gaussian surface there, Gaussian surface of radius R. Okay, now I need to kind of go through some of my logic, and this is going to be same as last time. So inside conductors, and this is for isolated conductors, okay, inside our conducting material, I know that E equals 0. And again, that's by the charged isolated conductor theorem. So review that if that's still feeling weird. That should, you should have that pretty firmly. So if E equals 0, then I can say if E equals 0, then I can say that flux equals 0. And that is by the definition of flux. If I look at this, the way that flux is defined, the way that we calculate flux, if E is 0, flux has to be 0. There's no way to get a non-zero flux with a 0 E. And I've mentioned this before, but I'm mentioning it again. The reverse is not true. So if flux is 0, that does not mean that E is 0. And you can think about why that would be in terms of the scalar product, mathematically, physically, whatever. So we have now that flux is 0, and I can say if flux is 0, then my enclosed charge is 0. And that's by Gauss's law. Gauss's law tells us epsilon naught times flux equals the enclosed charge. So if I know flux is 0, epsilon naught's a constant, right? So then Q enclosed has to be 0. All right, so that is all really solid. This is what I base my next part of my analysis on. So if I know that my enclosed charge has to be 0, and I know that in this middle cylinder, I have a positive lambda here, right? And my Gaussian surface, where it is right now, this green dashed surface, must enclose 0 net charge, then I know there must be negative lambda residing on the inner surface of this thing. Because it must be that I'm enclosing 0 net charge. And the only way that can happen, the only other place there is for charge to sit is on the inner surface of the cylinder. So since we were told that the cylinder, that the cylindrical shell has 0 net charge, that means that the outside of the cylindrical shell must have positive lambda sitting on it, which helps explain the outward electric field that we see when we look at the region outside the shell. So that's how we would answer the induced charge, that the inner shell, the inside of the shell has an induced charge negative lambda, so charge density, right? The outside of the shell has therefore an induced charge positive lambda. And I want you to think for a moment how that would be different. So let's just pause for a second, because both of the examples we've gone through, the outer shell has had 0 net charge. So we can walk through like how would that be different if it was a slightly different case. So I'm just going to add a page to this problem and talk through that, because this question when I teach in class always comes up. And I want to address it then. So let's go ahead and say, all right, we have I'm just going to freehand this. Not as pretty, I know. Here's our case, the cylinders. And I'm going to go ahead and put my Gaussian surface in. So I'm just discussing this same aspect of induced charge we were just talking about, okay? And what I'm going to say here is that let's let this inner cylinder have positive lambda. But now let's say, in this case, let's change something up. And let's say the outer cylinder has net charge density negative 5 lambda. Okay, so that's given. The outer cylinder has a net charge density of negative 5 lambda. So say it's not net charge 0. So how would this work? Well, we would go through the same logic we did before, showing that our Q enclosed would have to be 0. And what that means is that you still must have negative lambda on this inner surface. So changing the net charge of the outer cylinder doesn't change the charge that resides on the inner surface, because the charges inside my Gaussian surface still have to sum to 0, regardless. They still have to sum to 0. So what it does change now is what charge must be sitting on the outside of the shell, because now we know we have this total negative 5 lambda on the shell. So if negative lambda is on the inside, that leaves negative 4 lambda to hang out on the outside. So this would be a different case. So if I have now a shell with negative 4 lambda on the outside, my electric field's not going to be radially outward. My electric field for this thing is now going to be radially inward, right? So that would have a quite a different outcome. Even though the inner rod is still positive, the fact that when you look at this whole enchilada, the inner rod and the outer rod, the outer cylinder, the net charge of the whole thing would be negative, right? And you would see that if you were to, when you analyze the region outside the cylinder, because you would enclose a negative net charge. So you would see that your flux would have to be inward. So last thing I want to add here, just um, while we're discussing that, is taking another look at Gauss's law real quick, which tells us that epsilon naught times flux equals enclosed charge. So this enclosed charge here includes the sign, right? This is an algebraic sum of my enclosed charge. That includes sign. That can be positive or negative. So that means that the left-hand side of this equation, the flux can be positive or negative as well. So remember the definition of flux here, E dot dA. So think about it. How would you have a negative flux? That has to come from the scalar product. So if E and dA are in the same direction, that's always going to render something positive here, yeah? But when I have E and dA in opposite directions, your scalar product renders negative there. And that will happen in the case of negative enclosed charge. And if we were, for instance, analyzing the region outside this, and I put my Gaussian surface out there, you can see that E, and then I'll draw in my dA. dA is always outward normal, always, always, always. So my E and dA are going to be in opposition. My E and dA are going to be in opposition. So you can see that right here. And that will render a negative sign when I calculate the flux, which will match with the negative sign of my Q enclosed. So when you're applying Gauss, never ever ignore a negative sign, or you should never have different signs on either side of the equation. The signs on both sides of the equation must match. And that, in fact, can be a clue to you that you've done something wrong, or that you've neglected the direction of E or dA in your flux calculation if you have a sign inconsistency there. Okay, so that's all I wanted to add there. All right, we've gone through 2 good symmetries, and hopefully you have a much better feeling for Gauss's law application.